Welcome back. In this video, I'm doing Leetcode problem 476, number complement. It's in Leetcode easy. So the complement of an integer is the integer you can get when you flip all the zeros to ones and all ones to zero in its binary representation. For example, 5 is 101, and its complement is 0, 1, 0. So 1 to 0, 0 to 1, and 1 to 0. Okay, which is to give an integer number, return its complement. There are various approaches for this. We have few like one-liner approaches, but I'll do a bit longer one just to explain the idea, and then we can show the one-liners. So the first thing to do in this problem is to find what's the length of binary representation. So there are like various ways to do it. I'm going to do it with a loop, so I'll start with length equal to 0. And while yeah, two, so let me first explain. How do I know what is the length of uh, of this number in binary representation? So number of bits is required to write the number. I do it by checking if the number can be if the num is, so we need to find exponent 2 on some exponent. So first time that value is bigger than this. So for this it will be 5, and 2 to which number is so 2 to the 3 is first number that is greater than 5, because 2 to the on the exponent 2 is 4. I'm not sure what's the English term for 2 to the something, 2 to the power. That's what I was looking for. So 2 to the power of 2 is 4, and 2 to the power of 3 is 8, and 5 is in between. So it means we need to have three bits to represent this 5. So while 2 to the length is less than num, if it is num, so num is like, let's say 8, then we need to give it, then its complement is just number minus 1, but we're gonna settle that later. And we also need to check, let's see, so for 1.0, yeah, okay, it will work. So we just increase length by 1 here, and we need to, so we need to check if num is equal to 2 to the power of length, then we just return num minus 1, and if it's not, we return, so 2 length. This will be the number, this number minus 1 is the greatest number we can write, because 2 to the 3 is actually 1 bit, requires 1 bit more than length to write it down. Because we have bit 0, bit 1, bit 2, bit 3, and so on. So 2 to the length minus 1 is to get, like in this example, 7, and 7 is the biggest number we can write with 3 bits. And we just need to take nums. To length, okay, let's try. Not nums, but num. Is submitted, that should be good. And okay, it works. But let's also do, so this part was just just because we needed to check the the number of bits required to build this number, but and maybe this solution was even a bit bad. Yeah, I think it's bad, while it's also equal. Yeah, now it came to my mind, because if we use this, then we don't need to use this part. This should now work. This should also work, because if it's equal, then it's one bit more. So if you understand, because it's equal, so when length is 0, we have 1 bit. If length is equal to 1, let's say we have 2 bits, and with 2 bits, since we are looking like, how to explain it easily. So when we check if it's only less, so if it's this case, so if our number is equal to num, we won't do this, and we'll have here, we'll get the number with this, but I'm not sure how to explain it. Let's just show. First, let's check if it works. So let's see. It should be good, I think. And yeah, it's good. So what's the problem? So before I use this, and in this case, if we had like 8, we would have 2 to the, so 3, that wouldn't be less than none. And we'll have 3 here, so we have 8, and we'll have here 8, and then this one would be like out of order. But if we say less and equal, we'll actually find, so in this case we only find length, number of bits required to write it, or numbers that are like not how can I say, that are not so each number that is 2 to the power of something, so 1, 2, 3, 4, and so on, the power, so 2, 4, 8, and so on, it requires one more bit than all the other numbers between. So if, let's say we had 5, so for 5 and 8, in this case, we would require same number of, we would get the same length, but length is actually not equal. So length for number 8 is 4, not 3. So we need to do this to get the exact number of bit it requires. So I hope this makes sense. I'll just submit again to check if it's okay. And this way we actually implemented that bit length part. Now that we know bit length, we can do it like how we calculate bit length. We can do it in one-liner. So just return 2 to the power of nums dot bit length for bit length. I'm not sure. Let me check it out. Okay, so yeah, it should be bit length. 2 to the power of number of bit length. So -1 minus none. This should be the same thing. Let's try to run it. Submit. Okay. Other approach is we can use exclusive OR. So how would we use exclusive OR? We would just shift, so 1. We shift it by the number of beats. We shift it by number of beats, like let's say we have 5, so it will be 3. So this will be 8 minus 1, that's 7 minus 9, okay. Should be also correct. Yeah. And like other approach would be so instead of this, we store it. So XOR num, but we need to do it like this, I think. So to get the so we get the form. Yeah, yeah, should be good. So let's try to submit this one also. And yeah, it works. Okay, I hope this made sense. Thank you for following in this one, and see you in the next one. And I almost finished without complexities, so time complexity and space complexity complexity. The space is of 1, and that's easy to get, but time complexity, as we could see from like previous one we did, I think that should be this one. Oh. So it's of log n because this while loop will have it log n times. That is something I wanted to show. So let's go back to the problem. And yeah, so time complexity log of n. Okay, now for real, thank you for checking this one out, and see you in the next one.